Okay, let's go through our first problem. Magnesium is added to 250 milliliters of 0.5 molar HNO3. For right now, this is excess information that we don't really need, but you're going to see that as we go through because obviously we could be doing stoichiometry with these type of problems. So in order to write the single replacement reaction, we need to get rid of the spectator. And so the spectator in the type of single replacement reactions that you need to do, the cationic ones, is always going to be the anion in the compound or the anion in the acid. So in this case, we have a compound. And this is actually one of the most critical steps. When you get rid of the spectator, you need to remember that whatever is with the spectator has a charge because it's part of a compound. And so we immediately come in here and make this Ag+. That is really a critical step. So now what we're going to do is come down here and we are going to predict the products if this actually reacts. We don't know if it reacts, but so magnesium plus Ag plus, right? Super critical. Always go back and check the thing that was in the compound is what has the charge. So now it's going to react. So this is going to be different than what's listed up here. This is going to be transformed because a reaction takes place. This is where magnesium will be transformed into magnesium 2+, and silver will go to Ag. Well, why is this Ag 2+ here? This is Ag 2+ because in the periodic table, it's in group 2, and all group 2 metals, when they get a charge, will be +2. Okay. So now we need to figure out if this actually reacts or it doesn't react. And so what we will do is we will write the half reactions and figure out the E cell value. So let's go ahead and do the first one. So that's going to be magnesium. Now magnesium is losing electrons. We know it's losing electrons because it's becoming 2+. And if it's losing those electrons and giving up those electrons, we put it on the product side. And this is known as oxidation. So I'm going to put ox here so we know this is the oxidation half reaction. And we know that it's 2 electrons here because the magnesium goes from Mg to Mg2+. The charges should balance out. So the 2+ here and the 2 electrons are negative. They should balance out to equal 0, which is what it is on this side. And now we're going to go to our reduction potential chart, the yellow sheet of paper. Oops. And let's see here. We've got magnesium, and on the chart, the reaction is flipped over because this is not written as a reduction, but instead it's an oxidation. So not only is the reaction flipped over, also the sign is flipped over for the E value. So on the chart, it's negative 2.37, but because we flipped it over, we're going to make it positive 2.37. Okay, so now we have our oxidation oxidation reaction written. Now we're going to do the reduction half reaction. Reduction. It's going to be the silver because something has to get oxidized and something has to get reduced. So silver is gaining 1 electron, and it's only gaining 1 electron because it's going from plus to silver 0. Remember, when it's an element, it has no charge. So we're going to look this up on the table, and when we find this, since this is written as a reduction and the table is a reduction, then the value of the number does not get flipped over. So when I found it on the table, it was 0.8, and I'm going to leave it as 0.8. All right, so now we're going to add these two together, and we get E cell equals 3.17 volts is the unit. And this is obviously a positive number, so the reaction does occur. And I'm going to put a square around this because this is one of the values you're going to need as we go. And since the reaction does happen, we're going to come up and we're going to balance the electrons. And what we mean by that is we can only add these reactions together if the electrons are the same, that they cancel out. And so we've got 2 electrons up here in the oxidation reaction and only 1 in the reduction. So I'm going to multiply this whole reaction through by 2. Now the electrons cancel out, and we can add it together to get our net ionic equation. So net ionic just means that we're not putting the spectator back in. So we're going to get Mg plus 2Ag plus gives us Mg. And it doesn't matter which order, the magnesium 2 plus could come first, or the 2 silvers could come first. Okay, and that's our net ionic equation. And so all we have left now is to translate this into an actual Beaker diagram. So what really happens in this reaction? And I'm going to go ahead and clear the screen. So if you hold on 1 second. All right, so now I have the reaction. I just put it up here so that we can actually see everything. And that's just transferred from the screen before. And I've also started to set up the Beaker diagram. So when you have a Beaker diagram for these, you're going to have a beaker that contains your solution, and that's what's right here. And if you notice, when you have something in solution, you always want to break them up into ions because they're dissolved, right? Back to intermolecular forces and how we drew those IMF interactions. So we aren't drawing the water molecules just because that's too much to illustrate, but we know that they're there. The ions are separate, which is super important. The spectator ion should always be drawn in the Beaker diagram, even though it's not transformed, it's in there. So we have a piece of magnesium metal, and I'm just representing that by a rectangle since it's just a piece of metal. And we're going to draw a little arrow because it's getting put in. And this is what it would look like before the reaction. So the magnesium is separate from the silver ions. As they react, what happens to the magnesium? Well, now the magnesium is not magnesium, the element. It has been transformed into magnesium, the ions, and the nitrate is still just hanging out in here. So the things in green here are dissolved. So you actually won't see them. They didn't disappear, and they definitely didn't turn into a gas. They're in there. They're just dissolved. So you don't physically see them anymore. And then usually I'll make some sort of little pile down here just to indicate it's a solid. And this would be the silver metal. Once it turns to silver, the element, right? Because that's right. It's right here in our product, silver, the element. This is silver 0. That's no longer going to be soluble in water, and therefore it's going to precipitate out. It'll be some sort of chunky solid or powder or something like that, but it'll be a solid sitting at the bottom. And then this is what your Beaker diagram looks like. And that is the final step in completing single replacement reactions. All right, so I have a second example problem here. Gold is added to copper 2 sulfate solution. In this problem, if I was giving this to you on a test, I would have to let you know that when gold takes a charge, it takes a 3+, because that wasn't one of the ones listed on that second yellow sheet. But anyway, so that's what it would take. So we're going to get rid of our spectator ion. That's our first step. I guess really our first step here is going to be to write this as CuSO4, 1Cu, 1SO4, because this is 2+ and this is 2-. We're going to get rid of the SO4 and then put the 2+ immediately here. So we have gold plus Cu2+. Remember, always make sure one of them has the charge. So whichever one is in solution in the compound. And if this was to react, it would create gold 3+. And you would have to be given that information because we don't readily know that one. And then copper, the element. So let's see if this reacts. So in this case, it would be the gold, which would be getting oxidized. So it'd be Au losing 3 electrons. And if it's losing 3 electrons, we put them in the product. And now we need to look this up on the sheet. And gold is pretty close to the top. And so this would become -1.5. When I found it on the sheet, it was +1.5. We flip it over because we always flip over the oxidation. Half reaction. And now we're going to do the reduction. So reduction. And that's going to be copper 2+, and that needs to gain 2 electrons. And that would become copper, the element. And when I look that one up, you got to be careful with copper because there's a bunch of coppers. It's listed as 0.34, which is positive. But when we add this up, when we find this total, this gives us negative 1.16 volts as our overall E cell. And so when you get the negative value for this, what that basically means is that it's not going to react. And so let's come back up to here, cross this out, and we basically write no reaction. Okay. And if you were to draw a Beaker diagram for this, when there's no reaction, there's no need to, but I'm just going to draw a really quick one. You would have copper in here floating around with some sulfate ions floating around. They're in solution. And I'd have a piece of gold. And I would put this in. And because this doesn't react, what would basically happen is you would have a chunk of gold exactly how you put it in, sitting at the bottom. The copper 2+ would still be in solution. And you basically wouldn't see any change except for that the gold had gotten a little bit wet. All right, moving on to the next problem. All right, so this next problem is just a little bit different. Still going to handle it the same way. Here we have an acid instead of having a compound. And so again, it's still the anion that's going to be the spectator. And always when we cross out the anion, right away we're putting the charge. The only real difference with hydrogen ions is that it's not going to produce a solid metal. It's going to produce hydrogen, which happens to be a gas. It also happens to be diatomic. So when we go to predict this, we've got calcium plus, and that's calcium 0 because it's the element, plus H+. And for this one, the one thing you want to do is right away you want to put a 2. And the reason why is because if hydrogen becomes a element, it's not just going to be H, it's going to be H2 because of it being a diatomic. And really working with acids, that's the only extra little kind of trick to get this to work out. And then we have calcium 2+. All right, so in this case, the calcium is getting oxidized because it's lost electrons going to 2+. So we've got calcium going to calcium 2+, plus 2 electrons. And we're going to look this up on the table. This one's pretty close to the bottom. And when I look it up, it's negative 2.87 volts. I'm flipping over this because it's an oxidation half reaction. And I'm going to change colors here. Reduction is going to be, so again, when you write this one, you have to be careful. It has to be 2H plus 2 electrons. And that's how you'll find it on the chart. So that'll remind you, but just because it's making H2. And this one is 0, because actually it turns out all of the reduction potential tables are actually based off of this one. They're all in comparison to this. And we add the two of these together, and we're going to get a positive 2.87 volts, and that's going to be our E cell value. And that's positive, so this reaction will happen. And when we look up here, we will notice that the electrons are the same, so they automatically cancel out. And so for our final reaction, we are going to get, we didn't have to multiply anything here because they already canceled. And we get calcium 2+. And all I'm doing here is I'm just taking what I have here and just bringing it down so that it's all one reaction. And this is again known as a net ionic because it doesn't have the spectator in it. And truthfully, we don't really want the spectator in there because it doesn't react. And I think for this one, I'm probably going to be able to squeeze the Beaker diagrams in. So when we draw the Beaker diagrams, start with beakers. They don't have to be beautiful. You can draw squares too, if that works better for you. And in solution when you start out, so that needs to be with whatever you have here. So that's going to be H plus. We do have to remember the spectator here because it's always good to put it in solution because it truthfully is in there. And the calcium isn't yet in the solution, right? Because it's still a big chunk up here. And you can draw this however you like. This is being added in. And now this is going to react. And I'm going to change colors just so it stands out a little bit. And so after the reaction, this is now calcium is in solution, so you no longer can see it. It's no longer a chunk. But again, it didn't disappear. It's just in solution. Now it's dissolved because we can't see dissolved ions unless they have a color and calcium doesn't. Now, hydrogen is not going to sit at the bottom because hydrogen is a gas. So the second thing that's kind of different about acids is instead of creating some solid sitting at the bottom, we're going to draw bubbles coming up and label them as hydrogen gas because that's what you would actually see visually in a reaction. All right, we're going to do one last practice problem. So now we've walked through an example with an acid, and we're going to do a second acid problem right now. All right, so this is another example of a metal. Mercury is kind of a weird example because obviously we would never work with it, but I want to save some of the practice problems for the ones that you'll actually see in lab. So mercury is added to 1 molar HCl. All right, so mercury is one you also probably don't know the charge for, but generally it'll take a 2+. So we are going to get rid of our spectator, and that's the Cl, and the second that we do that, we're putting that plus charge. So what would get oxidized here is the mercury, right? So, oops, mercury is an H, not an M. Take that away. Okay, so Hg is mercury, and we would add that to 2H plus, and that would give us hydrogen, the element, and mercury is 2+. You probably didn't know that, and that's okay. One of the ways, if you get stuck and you're not sure what it would turn into, if you use your reduction potential sheet, most of them only can go to one thing, except for like tin, lead, and iron. So they're pretty easy to figure out what they would be based on that sheet. Okay, so now we have the predicted products if it reacts. And now we're going to write an oxidation half reaction. And that would be the mercury losing 2 electrons because it goes to 2+ plus 2E. And we'll look this one up on the table. And that is going to give us negative 0.85 because when I found it on the table, it was positive. And when I write the hydrogen, there's another one on the table that has an interesting mercury complex. So you wouldn't use that one because remember, we're always using the one that goes to from the ion to the element. So this probably wouldn't be one you would see on a test, but just to give you an example. Here, so we've got then the hydrogen reduction. So 2H plus 2 electrons. And again, the only reason why it's 2 is because hydrogen is diatomic, and since it's going to make H2 on this side, you need 2 on both sides. And this is 0. And when we add this, we end up getting negative 0.85 for the E cell value. And because this is negative, that means we come up here and these two things will not form. We're actually going to get no reaction. Okay, so basically just nothing would change. So you would not get hydrogen gas. The mercury would just sit in the bottom of the beaker with the acid and roll around in there. All right, so I hope this tutorial has helped. And now you can work on your practice problems, or if you're doing this, watching this again to work on your labs. And if you need to go back and you can rewatch these and pause, they are available.